This chapter is going to consider the main ideas of deep learning and deep network without complex computations in layman's terms. Experiments with real data confirm in some ways they can or they cannot theoretically give you an advantage of deep neural networks over shallow ones by metric definition and comparison. The task at hand is classification. We shall create an indicator and an expert advisor based on a deep neural network model and working in conjunction according to the client-server scheme, and then testing these throughout in an iterative fashion. Third generation neural networks are based on second generation neural networks with the exception of that sigmoid function on the hyperbolic tan of the upper skew symmetric matrix of identity values. The way of information processing is greatly affected by the absence or presence of feedback loops in the network. If there are no feedback loops between neurons, the network has a structure of sequential layers where every neuron receives information only from the previous layer. Information processing in the network is unidirectional. An input signal is processed by a sequence of layers and the response is received in the number of tags equal to the number of layers. Presence of feedback loops can make the dynamic of a neural network, in this case a recurrent neural network, unpredictable. Actually, a network can loop forever and never produce a response. At the same time, according to Alan Turing, there is no algorithm for an arbitrary recurrent network to identify if its elements are going to get into equilibria, aka the halting problem. Generally speaking, the fact that neurons in recurrent networks participate in processing information many times allows such networks to process information at a deeper level in different ways. In this case, special measures should be taken so the network does not loop forever. For instance, use the skew symmetric case. The symmetric connections, like in a Hopfield network, or forcefully limit the iterations number. With no feedback loop, a multi-layer perceptron. Without a supervisor, a competitive network of self-organizing maps featuring data compression, dynamic programming, and feature separation. At that layer, we are clustered into the Keras and TensorFlow libraries within your R distribution library. And if we think about a Jordan network as being partially recurrent, and partially recurrent is quite similar in terms of a soft minima of an Elman network with an energy gradient. It can be treated as a feedforward network with additional context neurons in the input layer. These context neurons are fed by themselves, direct feedback, and from the input neurons. Context neurons preserve current state of the network. In a Jordan network, the number of context and input neurons must be the same. Elman networks are partially recurrent and quite similar to Jordan networks. The difference between Elman and Jordan networks is that in an Elman network, context neurons are not fed by output neurons but by hidden ones. Besides, there is no direct feedback in context neurons. In an Elman network, the number of context and hidden neurons must be the same. The main advantage of Elman networks is that the number of context neurons is defined not by the number of outputs like in a Jordan network, but the number of hidden neurons, which makes the network more flexible. Hidden neurons can be easily added or taken away, unlike the number of outputs. In this feed-forward neural network that contains an intermediate hidden layer of radially symmetric neurons, such as a neuron converts the distance from a specified input vector to its corresponding sensor by some nonlinear law commonly taken to be Gaussian, this network would have the advantage over multi-layer feed-forward networks. First of all, they emulate, not sure about the word, an arbitrary nonlinear function with only one intermediate layer, which saves the developer a necessity to decide on the number of layers. Then parameters in the linear combination in the output layer can be optimized with the help of widely known methods of linear optimization. The latter work fast, n log n. Not many, you can find a local minima quite easily. Depends if you're feeding the hidden layer a stochastic variable. I rather keep it algebraic. In terms of just building an arithmetic interpretation of outputs, that is just flexible, and in a corporate sense, it will allow you to build a pipeline at production level for you to start putting out a product and become profitable at the same time. A hot-filled network is a fully connected network, is a symmetric deep neural network. The main difficulty here is the curse of dimensionality. When input dimensions have to split up into layers using TensorFlow and Keras, we're going to add a noise algebraic interpretation of a Gaussian or a Boltzmann naive probability interpretation task scheduling. We are inspired greatly by the work of graduate students at the University of Toronto, led by Professor Geoffrey Hinton, who won the top prize in a contest sponsored by Merck. Using a limited dataset describing the chemical structure of 15 molecules, Hinton's group managed to create and apply a special program system that defined which of those molecules was most likely to be an effective medicine. The peculiarity of that work was that the developers used an artificial neural network based on deep learning. As a result, that system managed to carry out calculations and research based on a very limited set of source data, whereas training a neural network normally requires a significant amount of information put in the system. Hinton's team achievement was particularly impressive because the team decided to enter the contest at the last minute. Added to that, the deep learning system was developed with no specific knowledge about how the molecules bind to their targets. Successful implementation of deep learning was yet another achievement in artificial intelligence development of the eventful 2012s. So in summer 2012, Jeff Dean and Andrew Ng from Google presented a new image recognition system with accuracy rate of 15.8%, where to train a cluster system of 16,000 nodes, they used the ImageNet network containing a library of 14 million pictures of 20,000 different objects. And last year, a program created by a Swiss scientist outperformed a human in recognizing images of traffic signs. The winning program accurately identified 99.46% of the images in a set of 50,000. The top score in a group of 32 human participants was 99.22%. And the average for the humans was 98.84%. In October 2012, Richard F. Rashid, a coordinator at Microsoft Scientific Programs, presented at a conference in Tianjin, China, a technology of simultaneous translation from English into Mandarin by a simulation of his own voice. All these technologies demonstrating a breakthrough in the field of artificial intelligence are based on the deep learning method to a certain extent. The main contribution to the deep learning theory is being made by Professor Hinton, a great-great-grandson of George Boole, an English scientist, founder of the Boolean algebra underlying contemporary computers. The deep learning theory supplements ordinary methods of machine learning with special algorithms for the input information analysis at several presentation levels. The peculiarity of the new approach is that deep learning studies the subject till it finds enough informative presentation to account for all the factors that can influence parameters of the object in question. And this way, a neural network based on such an approach requires less input and information for learning, and a trained network is capable of analyzing information with a higher level of accuracy than usual neural networks. Professor Hinton and his colleagues state that their technology is especially good for searching peculiarities in multidimensional, well-structured arrays of information. The artificial intelligence technologies, particularly deep learning, are widely used in different systems, including the intelligent personal assistant, Apple Siri, based on the nuanced communication technologies and recognizing the addresses in Google Street View. Nevertheless, scientists are estimating success in this sphere very carefully, as the history of creating an artificial intelligence is full of optimistic promises and disappointments. In the 1960s, scientists believed that it would take only 10 years to create a fully featured artificial intelligence. Then, in the 1980s, there was a wave of young companies offering a ready-made artificial intelligence, quote-unquote, followed by a quote-unquote ice age, which lasted up to recently, thanks to Google. Now, today we have wide computational capabilities available in cloud services with Mesos and Kubernetes,